Hello, my name is Rafael. I will present a brief overview of the research that I did at the LMMP for my master's dissertation at PUC-Rio. My research is about the evaluation of equivalent permeability in 3D Vuggy porous media using Brinkman model. This research was done under the advisor of Professor Marcio Carvalho and co-advisor of Dr. Federico Carvalho. So, the motivation for this research comes from multi-scale reservoir models in which computed petrophysical properties on a smaller scale are used to feed simulations on a bigger scale. By using the computed properties of microscale models as input to macroscale models, one should expect more accurate simulation results. This research focused on modeling the flow in microscale porous media, in which one of the main challenges is related to the approach chosen to model the flow in the Vuggy space. As you can see in this illustrative detailed view of a porous rock, the pore space is presented in different scales. Attempts to model the flow in micropores and macropores as free flow regions should lead to prohibitive computational models, since the level of detail needed to compute the flow in such disparate scales should be too extreme. So, one possible workaround to this problem is setting two subdomains according to the pore scale size. In that way, the micropores and the rock grains altogether are going to compose a homogeneous region called rock matrix, and the macropores the Vuggy space. Following this approach to tackle the problem, our goal is to quantify the equivalent permeability by numerically solving the field equations and also analyze the influence of the macropore structure on the equivalent permeability. So, the methodology begins by acquiring high-resolution images using computed tomography. Afterwards, the volume image needs to be segmented in order to fit the simulation constraints. Here, we are distinguishing two subdomains, the porous matrix composed by micropores and rock grains, and the Vuggy space composed by macropores. Then, a subvolume of the final segmented image is subjected to a single-phase flow simulation using the finite element method for solving Brinkman's equation. The domain is meshed with tetrahedrons and discretized with linear and quadratic Lagrangian elements for the pressure and velocity fields. The volumetric mesh generated with tetrahedrons are unstructured, and the subdomains within the mesh are defined according to the final binary segmented image. Now I'm going to briefly describe the achieved results. So, the velocity and pressure fields are effectively computed. Also, equivalent permeability is quantified using Darcy equation. We also performed a quantitative analysis of many different meshed domains. The equivalent permeability of these many domains were plotted as a function of macroporosity in order to have a grasp of how the equivalent permeability varies with macroporosity. Furthermore, the structural parameters of the many meshed domains were used to fit empirical functions capable of describing the variation of equivalent permeability among the domains. Here we show the empirical function that was most accurate. Finally, I would like to thank all funding institutions that made this work possible.